So I'll just quickly rush through, okay, because we have got enough details. Yeah. Am I visible?
Yes, sir.
Okay. So I'll just run through this topic because you have got enough idea about what I'm going to discuss. So what we have done is this was a project funded by GTRE, okay, and any component, if you look at welding joints cannot be avoided. Okay, they are very important. And the biggest challenges, so far, if you look at the testing, either we look at the global response. Okay, so we take a welded coupon, okay, we cut a coupon from the welded plate, and then we subject it to a tensile testing, and then we look at the global response. But when you go to the designing, the biggest challenge is how these local properties influence the strength, and how do they behave upon loading. And another big aspect is how your process conditions influences these local properties. So these are the important challenges. So if you look at the, I'm not from a manufacturing background, okay, I'm mostly from design. So I collaborated with Dr. Abhay Sharma. So if you look at typical weld region, so you have a parent metal, then you have a transition zone, or we call it a low temperature heat affected zone. Then you have a high temperature heat affected zone, and then you have a partially melted, and the center would be the fusion. These are the different zones present, and each one has got its own property, because when you weld it, your filler material would be quite different from your parent material, and because you're applying temperature, so that would influence a different kind of a grain growth, and you'll have a gradation in the grain sizes starting from the fusion zone towards the parent metal, and that influences the properties. So what we have done is how we can measure these properties over this zone using the DIC technique. And so if you look at the classical methods, you cut small micro samples from this weld zones, okay, and then you should have a miniature test setup to test them. But the problem is when you cut a sample and take it out from these individual zones, there is a stress relaxation, and it doesn't actually reflect the condition. Okay, because once you cut it and you take out the material, there will be a relaxation, and that can influence this behavior. And people also do a lot of micro hardness study, so they relate hardness to the Young's modulus, but we don't get the strength values. So these are the some of the techniques, but they have this inherent disadvantage, because it tremendously takes a lot of time to cut a small sample, okay, and you are relaxing it, and another disadvantage with micro hardness is it gives you only the surface hardness. It doesn't give you a hardness interior to the material. Okay, so that's also a disadvantage. So the knowledge of zone-wise property distribution is important for accurate modeling of the weld zone. Okay, towards designer. So if you look at if you ask the designer, The important thing is how this process parameter influences the zone properties, these local zone properties, and invariably these properties influences the strength of the joint. Okay, so basic understanding in welded structure is when I'm applying a load, it should break not in the weld zone, it should sort of break away from the weld zone. So that is how you ascertain the quality of the weld. Okay, always it should break away from the weld instead of breaking at the weld. So this I'm going to skip. Okay, so this is to establish a testing protocol to estimate both elastic and plastic properties over each individual zones involving DIC technique. So what we have done is we have studied the we have carried out the study in TIE 6-4 sample. Okay, both thin as well as thick samples. So conventionally in aero industry they use either thick or electron beam welding for both thin and thick. Okay, so this is the sample which we have taken it for EBW, electron beam welded. Okay, and the bottom one is for the tungsten inert gas thick welding. So this is a thin sample. You can see the thickness is around 1.2 mm, and the above one you can see the thickness is 3 mm. Okay, and another study also we have called laser cladded nickel superalloy. It is SU718. So all of these materials find applications in gas turbines. So the same setup. So we have used a 2D DIC. So this is the sample. Okay, and for thin samples we have used a clevis pin arrangement. For thick samples we have held between the hydraulic grips and we have loaded it. And you can see that we have used two-dimensional configuration. Okay, and this is 100 kilonewton fatigue machine. Okay, and we carried out the test. So our camera is a spatial resolution 248 cross 2448 cross 204. It's typically a 2K camera, and we took every 200 milliseconds the images. We grabbed it and we carried out the test at a rate of 0.5 mm per minute. So these are the test conditions, and this is the rate 300 images per minute. So many images we acquired during the loading phase. And this is the analysis methodology. So basically to explain, so this is the material model which we are trying to capture. Okay, within the proportional limit, it's straightforward. It's more like a uniaxial specimen, and beyond proportional limit, that's beyond yield strength. So simple power hardening law K into epsilon power n. Whereas this epsilon P is your plastic strain, and this is how we measure the plastic strain. This is the epsilon by Y is the total strain measured, and we negate the elastic strain. So elastic strain, what we have done is we have taken yield strength by E. So this is what this is how we estimate the plastic. So epsilon IY we get it from the DIC. I know what is the yield strength corresponding to each individual zone. We will figure out the stress strain curve upon E. It would be. And this is the microscopic examination. So you have a fine-grained HAC, and you look at this, the cross section of the weld, and you have a coarse-grained HAC. So coarse-grained means your grain size would be bigger because you are pumping in heat energy. Your grains would grow to a bigger size, and then away from the weld pool, if you go towards the parent metal, you will have a fine-grained HAC. Then you have so this is how your grain sizes vary, and this is the base metal both on the left and the right. You can see the grain sizes are very small. So for the, and this is for a thin sample. You can see this is the fusion zone at the center. This is a coarse grain HAZ, fine grain HAZ, and this is the base metal. So this is how you identify the different zones, and then what we do is we locate them. So both sides of the specimen, on the top and the bottom, because we assume it to be symmetric about the center of the weld, from the center of the well. So we identify it and using a microscope, we identify different zones as I shown in the previous slide, and we mark them. So physically, I know from the well center zone what would be my fusion zone, what would be my coarse grain HAZ, fine grain HAZ, and where the parent metal or base metal would start. So these are my designates. And this what happens because I am doing the measurement on the thickness phase. Okay, I'm not doing the measurement on the width phase, the front phase. In the thickness phase, I'm doing the measurement. So this is over a 3 mm. I'm trying to measure the strain. So that is the biggest advantage you have with an optics based techniques. Because if you are typically using a strain gauge, then I should have a strain gauge of size lesser than 3 mm to be bonded there. Okay, that's very difficult. But whereas this is for a 3 mm, subsequently, so this A, the image on the left portion, this is for a 3 mm thick specimen, and the on the right hand side you can see this is for a 1.8 mm thick. So even thickness doesn't matter in case of optics based technique. That's the advantage you have, and you can see that as you keep applying the load. So this is your fusion zone, and so this is your fusion zone. So fusion zone experiences lower strain levels, whereas your base metal experiences higher strain levels, and the final fracture always would be away from the fusion zone, typically in the base metal. That means a well seems to be perfect. Okay. So if I plot the variation of the longitudinal strain, so this is the direction I'm applying the load in the longitudinal direction, along AB I'm applying, it's in the y direction. And you can see how the strain levels are dipping as you move towards the fusion zone. So this is the base metal. Okay, this is your failure zone, typically where you see higher strain concentrations, and then it sort of goes down towards the fusion zone. So the basic question I was being asked is how does it compare with an extensometer? Okay, DIC comparison with an extensometer. You can see that the red one is DIC, and the blue one is an extensometer, and you have got a good. This is a global behavior. Okay, so I can take a window over all those grain sizes, so all those well zone, and then I average the strain. I can plot stress versus the average strain. Then this is what I'm going to get. And you can see that typically before the fracture, there is a discrepancy. So you have to understand DIC is more accurate than the extensometer, because extensometer only looks at the, it doesn't measure strain. You are estimating the deformation, and from the deformation, you're back calculating the strain. Okay. So in a sense, just before the failure, there is a deviation. So where we believe DIC is more accurate than your extensometer readings. And if you look at, this is what typically the different localized properties are. So we take base metal, plot stress or strain, and then we have the transition zone. Okay, then heat affected and the fusion. So base metal and heat affected, we have a transition zone, and you can see how typically the variations are. Okay, so base metal more ductile, whereas your fusion zone, if you look at it's more brittle, but it is very it has got very high hardness. Okay, that means its stiffness is also high and its yield strength is also high. So that's how the fusion zone is. Then the data extraction, if you look at, since we are following power law, so if you look at this curve, this is your elastic part, straightforward. So each localized stress strain curve we extract, and we fit a polynomial, the straight line, and get the Young's modulus. Whereas for your K into epsilon n, so we estimate the plastic strain. plot load versus plastic strain, so log plot, and you can estimate the constant K and the hardening coefficient En. So this is the fit. So because it is most likely, it seems to be like elastic plastic kind of a behavior. It doesn't have like a mild steel. It's more like an quasi brittle. So it seems to be like elastic plastic kind of a behavior. And you can see this is how so this is your weld center fusion zone, but your fracture has somewhere taken place in the just at the transition zone, okay, away from the weld center. So these are the variations of the properties. Okay, Young's modulus for different zones. You can see that not put what is that. So your yield strength is typically it is greater for the fusion zone. Okay, I have summarized. Okay, this is the summary. So base metal, if you look at Young's modulus, is around 110. This is a titanium alloy, and your fusion zone is around 101. So your Young's modulus is going down, your Poisson's ratio is increasing, but whereas your yield strength slightly increases in the fusion zone from 875 to 907. Okay, and these are the coordinating hardening coefficient. K is the strength coefficient, N is the hardening coefficient. So for different zones on along both the from the central line, so both is we have measured it and we have plotted it. So this is how the properties vary. Okay, not big. So it's around 10 GPa is the difference between the fusion zone and the parent metal. Okay, so it's quite considerable when you look at the weld. And this is for the TIG welded sample, thin sample. And again, you can see that HAZ to fusion zone, your strain levels are going down. And just in the HAZ, maybe in the transition, it sort of tries to, the strain concentration takes place and it breaks off. Okay. And same procedure, same process. And individual properties we have estimated. And then we have extracted the coefficients. You can see it's very close to the fusion zone. In the transition itself, it has failed. And this is a very, very thin sample. Okay, so we have made measurements in the thickness. This is the front part. Front part also we have captured the strain, and but over the thickness also we have measured it. And so this is also a curved sample. Okay, this is because they have taken it from a casing, from a static part in a turbine. So this is a curved sample. So that is why we have cut using wire cut EDM, and then we have put a clevis so that the self arrangement is there and your loading would be more accurate. And similarly, the zone wise properties. Okay, then but there is if you look at the literature, there is a considerable discussion whether after I weld, I remove the flushing of the material. That is the projection. Okay, the weld projection, I have to remove it, or I can retain it. Typically, they flush it if it's a thick plate. If it's a thin plate, they don't flush it because it can disturb the weld. Can disturb the weld. So for thin sample they don't flush it. For thick sample they flush it. So when the flushing is there, what happens is closer to the fusion zone, the assumption of uniform stress field no longer holds good because of the variable geometry there. Your stress becomes becomes non-linear. Okay, non-uniform, not non-linear, non-uniform. So there's a problem. So we have considered a uniform stress state, you have considered non-uniform stress state, carry out the measurements, and then this is what the variations look like. So when I consider non-uniform, if I include the total bead geometry also, because more material is there, your stress levels will go down. Typically, your Young's modulus also will go down. Your yield strength, your yield strength also will go down. So that's what happens when you consider the complete bead geometry. But if you remove the bead, then the problem is it could be a little bit high. Okay. So, and this is for a cladded samples, SU718, and you can see they have a rolling direction is mentioned, and then you have to do titanium thing, and they were cladded using a laser beam, and they have taken a sample in the transverse direction. You can see that, and this is your cladding zone, and this is your sample. And when I apply a load, you can see that how your strain varies over the cladding zone. Okay. So typically it is lower in the base metal, it's higher. So you can wonder why this is important. In a sense, how the localized properties get influenced by the process conditions. That is what they are interested in. And another big challenge is how do these zones behave under a fatigue kind of a loading? Because any gas turbine, if you look at it, is subjected to fatigue load, thermomechanical fatigue load. Okay, so they're very much interested with the time, how these zones behave and what happens to these properties. They degrade, they still remain the same. So that is what on continuation we are trying to take one more project on the fatigue behavior of localized zones. Okay, so that has been sanctioned. We are waiting for the funds. So that we would be pursuing it in the future. So and as a designer, you also know how much the variation in the yield strength is across these zones from parent metal to the fusion, and how much is in the young smallest the variation is. And you have a range of properties to work with. And the most conservative property you can take, and you can sort of feed into your design envelope, and you can extract the data. So that is what they are also interested. So the next challenge is how do these weld joint behave under high temperature, and at a high temperature and at operating temperature, how when I'm subjecting it to a fatigue load, what happens to this welded zones. So this is what typically they are interested in. Okay. So this is how we have used DIC, and this was part of an MTech student, two MTech thesis. We have also carried out high temperature studies of this. I'm not presenting it for want of time. So this is for a clad sample, base metal, how stress strain varies for a cladded zone, how do they vary? You can see that base metal considerably lower, your yield strength is, whereas for clad zone, your yield strength is quite high. And so this is a typical response, okay, after you clad. And these are the properties which we have extracted. And we also fitted this Holloman power law, the strength coefficient and the N. And so if you look at the yield strength, there's a considerable difference, almost 100 MPa is there between the clad zone and the base metal. Okay, so, but this is still is an ongoing. The biggest challenge is there is in case of a thin sample, there is a curvature. How do I account it for the curvature? Because that might also, because thin sample, when I'm loading it, when there's a curvature, additional bending can come in. So that can lead to non-linear response. How can I de-alienate this non-linear response, or how can I minimize it? That's another challenge. Okay, then this bead, the bead, weld bead, when there is a projection, then it introduces a non-uniform stress field. And now how I'm going to handle this? Because for thicker samples, they flush it, but thin samples, they don't flush. So then it is more close to service condition. So now what happens to this property? So that is, so that also needs to be studied carefully. And so if you look at the thin samples, so what we have done is we have taken a width comparable to the thickness also sometimes. So that is not recommended, because so then there are some, we have to carefully look at like higher specimen width as compared to the thickness of the specimen. So if I have a higher width, a very thin sample, what happens? Almost like a sheet. Okay, then how the strain would vary in the even in the width, in the face of the specimen, how the strain would vary, because a very thin sample. So that's another challenge. Okay, so the curved sample is always a challenge for measurements, even for DIC. So we need to look at the error it generates and how to delineate this error for towards accurate measurement. This is fine. It's an ongoing work. So you might ask, what is the necessity of such studies? The point is, DIC, if you look at, this is one application, okay? So you might have an higher temperature, you might have an, you might, suppose I know Pandey recently has published some work using DIC and tire testing, okay? So when you apply a load on the tires, how do they behave? So they do use a DIC for the measurements, okay? So then now the biggest challenge is you have large structures, you apply loads and how do they behave? So that's another question. And so there we use extensively the DIC for the measurements. So we do a lot of composite studies. So thin, stiffened panels, curved panels, okay, larger size. We have comfortably we have studied close to 400 by 200 mm kind of a sample. Okay, and so DIC is gaining a lot of importance, but still accuracy, from accuracy standpoint, a lot of improvement is required. From algorithm standpoint, a lot of improvement is required, especially how to handle the curvatures. Okay, so high temperature, then non-linear. The biggest advantage is entire stress strain curve I can get. Okay, it's not only DIC, I have only shown it for the static because mostly I work with static kind of application, static loading. But even fatigue, we have attempted, we have estimated for fracture studies. We have done a lot of studies on fracture. And then we also can use for vibrations. So what we do is we put it in an exciter and we lock the camera and the exciter so that there's out of plane displacement under vibration, okay, to especially for the mode shape measurements. We can use DIC. People have used it for large blade kind of a structure, okay, flap kind of a structure. So a lot of vibration applications, especially for mode shape. I know people use LDV. So, but DIC also can be used for the capturing the mode shapes. Okay, so this is mostly from static. Okay, material characterization. High temperature DIC becomes extremely useful, but still a lot of research is required in this direction. And if you look at the Western world, they are trying to come out with standards for optical measurements. Okay, and I know pretty much the optics is used for larger size samples. Even you look at the whatever the people are talking about nanomechanics. I know Pandey is working with nano beams. If you want to get the deflections, okay, the beams, okay, you can use an AFM. Okay, but AFM still it's very costly. But what people also try to use is they also use these DIC techniques to get the bending deformations. Okay, you can also measure the strains. So even for such I would say nano kind of a mechanics also people are using DIC. So both the spectrums comfortably you can handle. Okay, so with this, yeah, I am done. And if there are any questions, I would take it. Yeah.